Okay, so this solution video is for the papers 1 and 2 questions that we have on Doppler effect. Let's start with paper 1. Okay, question 1. We got a train sounding a whistle approaching a train station, and the observer is stationary at the station. They're not moving. So it says, what is true? Which combo of statements is true? So 1, frequency received is higher. The frequency received by the observer is higher than that emitted by the train. The source frequency, that is true because the train is approaching the observer. So it says approaching a train station where the observer is, and so when the train is approaching, that is a higher frequency. F prime, F prime is higher, and so by v equals f wavelength, the weight lambda prime will be less. And so frequency is higher, that is true. But then it says statement 2, wavelength received is longer than the wavelength emitted. No, that would be a shorter wavelength received, so not statement 2. And then 3, the speed of the sound received is not affected by the motion of the train. That is true. The speed of sound depends on the medium. Not 2, but 1 and 3 are correct. That gives us choice B. Okay, next question. Number 2, on approaching a stationary observer, train sounds its horn and decelerates at a constant rate. Let's finish. At time t, the train passes by the observer and continues to decelerate at the same rate. So which diagram shows the variation with time of the frequency of sound measured by the observer? So this is interesting in that it factors in an accelerating source. But let's remember that, first of all, what is true of frequency when it's approaching, when the source is moving and it's approaching an observer, and when it's receding from an observer. When the source is approaching an observer, then the observed frequency is higher than the source frequency. And when the source is receding from the observer, it's less. And then the bigger the difference in the speed, the bigger that shift is. So if the source is going fast, then f prime, like for instance, if the source is approaching quickly, then f prime is much greater than the source frequency. Well, not much greater, but greater than if it was moving slowly. And so it says that the train is approaching the station and is decelerating, is slowing down. So when it's moving quickly, the observed frequency is going to be greater than the horn's frequency. And when it's approaching, moving slowly, it's still going to be greater. The observed frequency will still be greater, but not as great. So I'm looking at choices B and D, because A and C show that the frequency measured by the observer is greater than the horn frequency, which is true, but it says that it's getting bigger, and that's not going to happen. Maybe if it was speeding up, it's not, it's decelerating. But then all of a sudden at time t, it passes the observer, and now it's moving away from the observer, and that means that the received frequency is going to be less than the source frequency, but it's still slowing down. So the slower the speed of the source, the smaller the difference in the frequency. Now let's remember the way the graph axes work. I can see that the frequency, the y-axis, is all positive, but there's the horn frequency, which is the dashed line. And so, like I said, the slower the smaller the difference in the speeds, the smaller the difference in the speeds, and the speed of the actual speed of sound, and the speed of the source. Speed of sound is fixed, is constant. But actually, I meant to say one thing and I said another. Let me fix that. So let me fix that. So yeah, the slower the speed of the source is, the smaller the difference is between f prime and f. And so this horn's frequency, that's the frequency of the source. And so as that train slows down, then the F prime is going to get closer to the horn frequency. If the train actually stops, then the Doppler effect is canceled, and the received frequency is, in fact, the source frequency. So the reason why I'm marking D here is because D is the answer. In B, we have the appropriate shift from greater frequency to lower frequency, but that lower frequency gets lower and lower and lower as the train slows down. And it's not. It just continues to decelerate at the same rate, so it's slowing down the entire time. So that's D. Okay, so here's number 3. Train's going in a straight line away from stationary observer, so the train's in motion, the source is in motion. And it says train puts out a sound of frequency F naught, and the speed is 0.1 v, where v is the speed of sound. What is the frequency is heard by the observer? So this is a moving source, so we're going to use that equation. So we have F prime, the observed frequency, is the source frequency, times the speed of sound divided by the speed of sound plus or minus the speed of the observer. And plus or minus depends on whether the relative motion is towards or away. And so if we're moving away, F prime is less than the source frequency. And so that means if we think about that fraction, we want the v over v plus or minus us, we want that to be less than 1. So then the F prime winds up being smaller than the source frequency. And if we want that speed factor to be less than 1, then we want the denominator to be greater than the numerator, which means I'm going to be adding the source frequency. So when we're receding, moving away, on the bottom there, we add the us. And so it says that the speed of the source is 0.10 v, where v is the speed of sound. So let's solve for F prime. And so we get that F prime is 1 over 1.1 F naught, and that would be B. All right, next question. All right, we got some C waves, but all waves follow the Doppler effect principle. So let's see what they got going on there. So we know the speed of the waves, and they arrive at the beach. We know the frequency that they get at the beach. There's a girl on a surfboard. She's moving at right angles to the wave fronts. So she's moving in a direction that is parallel to the direction of the wave. And that's shown in the diagram. Anyway, it says she observes the surfboard crosses the wave fronts with a frequency of 0.4 hertz. What's the speed of the surfboard, and what's the direction of the motion of the surfboard relative to the beach? So I would call this, it seems like that both the source and the observer are in motion, but the source is like whatever is pushing the waves at the ocean. And so the waves would be the equivalent, like if we're talking Doppler, the waves would be the equivalent of like the sound waves or the light waves. So for this is an interesting setup, but I would consider this a stationary source and a moving observer. The girl is kind of experiencing the waves, so she's going to be the observer. Okay, so moving observer, I'm just going to write down the equation. I don't know if I'm going to need it, but I'm going to write it down anyway, just as a point of reference. So we have the observed frequency is the source frequency times the speed of the waves plus or minus the speed of the observer divided by the speed of the waves. Now we know the speed of the waves. It's not the speed of sound. We're not talking about sound. We're talking about water waves. But it says that the sea waves move at 2 meters per second. And so we know the speed of the waves. We know the frequency when the waves get to the beach. That would be the source frequency. And it says the girl observes that the surfboard crosses the wavefront. So basically she's experiencing the wavefronts with a frequency of 0.4 hertz. So that would be like her observed frequency. That would be F prime. And so the question wants to know what's the speed of the surfboard and what's the direction of the motion of the board relative to the beach. I probably figure out the direction first based on how she's observing the frequency. So her observed frequency is higher than the source frequency. And so if the observed frequency is higher than the source frequency, you're moving towards the source. And so it's like, wait, the source, what's the source of the waves? Well, if the waves are coming from the ocean and they're going towards the beach, the source, I guess, would be the ocean. And so the girl is moving towards the source. She's moving away from the beach and she's going out to the ocean. So this would be towards the source. So the source would be like the source of the waves, which is kind of out away from the beach, the ocean. So that means that the girl is moving away from the beach. Okay, so now that we're moving away from the beach and f prime is greater than f, we can also figure out whether in the numerator for the v plus or minus u naught, or u o, for o for observer, whether that should be plus or minus. So in order for f prime to be greater than f, then that speed factor needs to be greater than 1. And Bill's always interrupting me. And so if it's greater than 1, then that must be v plus u naught in the numerator, not v minus u naught. So let's solve for u naught. It's not, it's u-o. Whatever, you know what I'm talking about. The u, the speed of the girl. All right. Okay, and we're trying to get the speed of the observer by itself. So I divide both sides by 0.1 to get rid of the 0.10 hertz on the right side. Okay. And we get a speed of the observer of 6 meters per second, and would be away from the beach. All right, cool. Next. All right, let's check out number 5. We have another train. Okay, so number 5, there are two things to consider here. There's the intensity and the frequency. And you might be like, what do you mean intensity? Intensity isn't a question of the Doppler effect. Yeah, it isn't. But it's really not that hard. I mean, we can kind of, like, let's talk about the intensity first, right? So you have a train that has a sound of a constant intensity, right? And then and you're at the station, and the train is approaching the station. So if the train is approaching the station and it's getting closer to the observer, wouldn't the sound get louder as it got closer? Like, absolutely. So the intensity does not change. It does change, so not A or C. And so, yeah, the intensity will increase. It'll get louder as it gets closer to the station. Now, for number 5, we have to be careful about how we consider this, because you might be like, oh, so the train is approaching the station, so the observed frequency is higher than the source. So observed frequency is higher than the source, and so that would be increases, and the answer would be B. Nope, the answer is D. We just have to read the question carefully, right? So, all right, observer waiting at the station detects frequency F observed. That frequency F observed will be higher than the actual source frequency. All right, and you're like, so, all right, so then why is it D? Why is F observed decreased? You just said that the F observed is higher than the source frequency. Right, but it says that the train is slowing down. And so as the relative speed between the source and the observer is getting smaller. So yeah, that relative speed between the source and the observer is decreasing. So the Doppler effect becomes less and less, to the point that if the train stops, right, if that relative speed decreases to 0 and the train has the same speed as the observer, meaning both at rest, then there is no more Doppler effect. And the observer just hears whatever frequency is coming out of the train. And so that, yes, the observed frequency is greater than the source frequency, but as the train slows down, that F observed gets smaller and smaller, like higher than source frequency, but less so until the train stops, and then F observed is equal to the source frequency. So yeah, as the train slows down, yes, that looks like year. Let me fix that. Yes. The observed frequency is higher than the source frequency, but less so until the train stops. So as that train is slowing down, that observed frequency, while it's higher than the source frequency, gets closer and closer, decreases towards the source frequency, and so 5 is D. This is similar to number 2, similar principle to number 2 with the frequency graph. Let's see if I can actually, let's bring us back to number 2. So how that kind of, like, as the train slows down, like, yes, when it's moving towards the observed frequency is higher, and when it's moving away from the observed frequency is lower. But as the train slows down, that difference in frequency becomes lesser until, if the train were to stop, then the observed frequency would be equal to the source frequency. So notice how on that graph for D there, how even though there's a shift in frequency, that graph is approaching the source frequency as the source gets slows down. Incidentally, let's see. Yeah, if the train were speeding up, it would be actually this graph, where there would be a difference in observed frequency that is higher than the source when approaching and lower than the source when receding, but that would be growing in value if the train was speeding up. So let's see, let me just make a note on that. Train speeding up. That's the graph of that. All right. Anyway, let's go back to number 6. Ooh, stars. 2 stars viewed with a green filter. The images are just resolved. What is the change to the angular separation and the resolution when the green filter is replaced by a violet filter? What does this have to do with Doppler effect? Hold on. Yeah, this isn't a Doppler question. This is actually a resolution question that we did not see in the other thing. So thanks a lot, QBank. But we did resolution. So let's actually do number 6. Noting, of course, not 09.5 Doppler. Doppler is 9.4 resolution. There we go. This is actually a really good question for resolution. It's good and it's not. I like the aspect of the resolution. I think the angular separation is a little bit tricky. Angular separation of the stars as seen from Earth or whatever, that is just where the stars are in space. That has no connection to the filter you're using. So yeah, if I have like 2 different stars and they have an angular separation, it doesn't matter what telescope I use, it's going to have the same angular separation. So angular separation of the stars does not change. So it's either A or D. But what about the resolution? And that's an interesting question. So resolution for a circular aperture, resolution is 1.22 lambda over B. Now, by switching out the filter for a green or green-violet or whatever color, that doesn't change the aperture, so that stays the same. But it does change the wavelength that's coming into the telescope. And so it's like, will there be a resolution change? And yes, actually. But it actually gets better with a violet filter. So basically, remembering that for colors, for Roy G. Biv, we know that red has a longer wavelength and violet has a shorter wavelength. And so actually, red would have a larger Rayleigh criterion angle. And so red would require the largest angle, and then violet would require the smallest. And and it says at green that these the stars were just resolved using the green filter. And so violet actually has a tighter Rayleigh criterion angle, meaning that you can get better resolution from violet than out of green, because the Rayleigh criterion, the smaller the angle, the better the resolution. So actually switching to a violet filter would give you better resolution. So if the stars were resolved at green, then they would still be resolved at violet. They would actually probably get an even crisper image using the violet filter. You'd be looking at different wavelengths, aspects of the star, whatever, but in any case, the answer is A. There's no change in the angular separation, and the resolution remains resolved. I would say, though, that if instead of switching to a violet filter, if I switched to a red filter, or anything longer wavelength than green, then no, it would no longer be resolved. So yeah, the answer would be D if you used a red and orange yellow filter or any lambda that was longer than the green wavelength. All right, next. Okay, number 7, ambulance siren. We have the source frequency, we have the speed of sound, we know the speed of the ambulance moving towards the stationary observer, so the source is in motion, and it wants to know what is the frequency heard by the observer. This guy is really straightforward. There's our equation. Source is approaching. So we're approaching, so f prime is greater than the source frequency, so you are going to be subtracting the speed of the source in the denominator. And there it is. F prime is 1200 times 330 over 290 hertz. Choice D. Next. Alright, so I have 2 spectral lines for hydrogen, and with increasing wavelength going to the right. So that would mean violet would be on this side, red would be on this side. And it says emission spectrums and measured by observer moving away from the gas sample. What are the correct shifts for the spectral line? So moving away, that's a red shift. And so red shift means the observed frequency is less than the source. With wavelength, it's the other way around because frequency and wavelength are inversely proportional. So the observed wavelength would be longer or greater than the source. And it says increasing wavelength is to the right, so I would want to shift the lines to the right. And again, increasing wavelength is to the right. So that is not A or B. And you're like, wait, both C and D show a redshift, so which is it? The other thing about the shift for frequency is that the shift itself depends upon the frequency. We can see that in the equation. I should be talking about wavelength because this is wavelength, but the shift depends upon the wavelength. It's the shift, delta lambda, over lambda is approximately equal to V over C. So the speed is constant, and so is the speed of light, but we can see that the delta lambda up on top in the numerator is relative to the wavelength itself. And so basically, the larger the wavelength, the bigger the shift. Like the longer the wavelength, the bigger the shift. Like violet will shift less than red will. So yeah, as the wavelength increases, there's a bigger shift. So the red line will shift more than the violet line. And so we're left with C. That the shorter wavelength line, X, is a shorter wavelength, and then Y is a longer wavelength. So not only do they shift towards a longer wavelength because of redshift, but the Y line with the longer wavelength will shift more than the X line will. So that's C. So then, all right, that is 8. And then here is number 9 of 12. I think there are 12 multiple choice in this set. All right. Okay, number 9. First of all, right off the bat, they're using C for the speed of sound, which bugs me. C is the speed of light, but whatever. I mean, they can use whatever letter they like. So it gives the train. The train is approaching with a constant speed. So the train is moving and the observer is not. So read that carefully. The observer is not moving. The train is. So the source is moving. And they're talking about a wavelength shift, which is going to be relative to the frequency by V equals F lambda, where V is C in this case. Here's my formula, and then we are approaching. So I'm going to, with the plus or minus US, I'm going to do subtract, because that gives me a smaller denominator, meaning that the speed factor is greater than 1, and I do want an F prime that is more than the source frequency. There's probably different ways of doing this, but I'm going to solve for the frequency and then just convert it to wavelength at the end. I'm going to have to solve for the observed frequency in terms of the source frequency, but that's okay. And I know that frequency and wavelength are inverses of each other, so if F prime is 34 F over 33, then lambda prime is 33 over 34 lambda, which makes sense. When the source is approaching, it's a higher frequency and also a shorter wavelength. So while f prime will be larger than f, lambda prime will be smaller than the original lambda. So yeah, lambda prime is 33 over 34 lambda. Now let's see. It says, what is observed speed of sound and observed wavelength as the train approaches? Well, the speed depends on the medium, so the speed's not going to be any different. So right out off the bat, we can eliminate B and D. And then the wavelength will have changed. I think that's obvious. Man, I did all that work for nothing. Just by process of elimination, it's A. But I don't know. It's good to have the work shown in the derivation. But yeah, maybe I should have talked through the choices first. Anyway, so that problem's a lot easier than I thought it was. A. Number 10, stationary sound source emits waves, wavelength lambda, speed v. The source moves away from a stationary observer, so the source is moving. And what are true of the wavelength and speed is measured by the observer, so I am moving away. And if the source is receding, we know that the observed frequency is lower than the source frequency, and so therefore the observed wavelength is longer. But the speed of the waves, am I reading this? Yes. The speed depends on the medium, like we just said in number 9. So the speed will not have changed. So that leaves us with choices A or C. And then the wavelength and speed as measured by the observer, that would be a longer wavelength, not a shorter wavelength. 10 is A. Okay, so 11. 11 has a reflection. I saw this coming. So when there's a reflection, you actually have to consider the both the pre-motion and the post-motion, pre-reflection and post-reflection, because when there's a reflection, like for instance, if this train sound bounces off the cliff face, at first the source is moving and the observer is the cliff face, but with a reflection, then the cliff face becomes the source, and then the train. Let's see, reflected back to the train. And I'm assuming that this is before the train turns the corner, because once the train turns the corner, then there is no relative motion between the train and the cliff face. So, reflected back to the train. Yeah, it doesn't forget about turning the corner. I think they just have that turn so that the train doesn't crash into the cliff face. Anyway, so yeah, with the reflection, the cliff face becomes the source, a stationary source, and a moving observer, and the observer is moving towards the source. So anyway, I'm actually, yeah, I didn't even move the question, so you're like, what am I talking about? Here is 11, okay. I was reading it off of my computer. I have my computer right here. So yeah, we have a train moving towards the cliff face, and then it reflects off the cliff face. So let's see what we have here. Speed of sound in air is c. Again with the c. Whatever. So the speed is c. I guess it's like a constant, so they're just using c. I'd prefer they used k, but no one asked me. And it says, what's the deal with the whistle frequency? So let's break this in half. I'm not even sure that we're going to need to break it in half, but that is the appropriate way of handling Doppler questions involving reflection. So let's take a look. So we got a moving source and we're approaching. So if we're approaching, that means the frequency needs to be higher, so the speed factor needs to be greater than 1. So my denominator is subtracting. And so that is the frequency that is received by the cliff face before the reflection. But then that higher frequency, that wave of a higher frequency, then reflects off of the cliff face. So now we have the cliff face is the source, the train is the observer, and they are approaching. And to avoid confusion, I'm going to call the original f prime from the first leg, I'm going to call that f prime. But for the second leg, I'm going to call that f double prime, because that source frequency, quote unquote source frequency, is actually the reflection from the first part. And again, we're still approaching, and so the observed frequency is going to be higher than the source, and so I want my speed factor to be greater than 1, so I'm going to be adding in the numerator. And so our f double prime is f prime times c plus uo over c. Now us and uo, that's the speed of the observer and the speed of the train, the speed of the observer and the speed of the source. Those are the same, so I can get rid of the uo and the us. Sorry, by get rid I mean of the of the subscripts. They're just u. All right, so f double prime. I'm moving down here. So f double prime is f prime c plus u over c. F prime from the top up here, f prime, is the actual original source of the train whistle, f times c over c minus u. So when I combine the terms together, that's what I get in terms of the f double prime from the reflection, in terms of the original frequency that came originally. And so when I multiply all this together, I can see that these two c's cancel, and so f double prime winds up being c plus u over c minus u times f. And that is choice A. Naturally, when working through these solutions, you want to maybe avoid any kind of notation that gets to fu, which is what you might think if you actually saw a problem involving reflection and the Doppler effect. Dum-dum. So a train traveling in a straight line emits a sound of constant frequency. Observer at rest, we have a traveling source. At rest, very close to the path of the train, detects a sound of continuously decreasing frequency. So I said, what is the train doing? So we have a source is traveling. The train is the source, and the train is traveling. So we have a moving source, a stationary observer, and they are approaching. Actually, I don't know that. Detects the sound of continuously decreasing frequency. Interesting. Well, okay. Well, we have, let's see. It's a moving source. So here's our moving source equation. And the denominator remains plus or minus because I don't actually know if the train is moving towards the source or away from the source. But let's consider all of the, all the different options. Well, first of all, if the frequency is changing, it says continuously decreasing frequency, then there is, and it says the frequency there's a frequency shift, but the frequency continues to shift. So there's a continuously decreasing frequency. Then the difference between the source and the observer, that speed difference is not constant. If that were a constant speed, there would be a frequency shift, but then there would just be a shift, and then that difference, that shift would be constant. And it says that the frequency itself is changing over time, so the relative speed is not constant. So we don't have A and we don't have C. But we still got to figure out if we are approaching or if we're moving away. Notice that both choices say increasing speed. So let's consider that. So we know that when the source and the observer are approaching each other, the observed frequency is higher than the source frequency. And the bigger the difference in the speed, the bigger the difference in the frequency. And we can see that in the formulas, that it's if the speed of the source were 0, then the observed frequency would be equal to the source frequency. You would have f prime equals fv over v, which is 1. But then the plus or minus speed of the source factor, whether it be add or subtract, the bigger the speed of the source, the bigger the shift in the frequency. So if I have an approaching source that's a higher frequency, as the speed of the source increases, then that frequency would be bigger, the difference would be bigger and bigger and bigger. So basically, to kind of expand on Doppler effect, what happens, like we know what happens if you are approaching at a constant speed or receding, moving away at a constant speed. But let's expand upon that. Suppose the source is approaching and the speed of the source is increasing. So not just approaching, but also speeding up. So if you're approaching and the speed is increasing, then f prime is greater, like the received frequency is greater than the source frequency, but also the received frequency is increasing. So not only is it, oops, sorry, I had the wrong, yeah, f prime is greater than the source frequency, but then also it's going to be greater and getting greater and greater and greater if the speed of the source were to increase. Now, if you are approaching and the speed of the source is decreasing, if it's slowing down, then f prime is still greater than the source frequency. However, that f prime is now decreasing. We saw that in two other questions. I think there was that graph question in number 2. And so it's like you have, it's decreasing, and then, let's put it this way. So decreasing and if that speed decreases to 0, if the source stops, then there's no more Doppler effect, and f prime decreases down to just equal the source frequency. So yeah, if you're approaching and you're speeding up, the f prime is greater than the source frequency and then steadily increasing, and then assuming a constant acceleration. And then if the speed of the source is decreasing, then f prime is greater than the source frequency, but it's getting closer and closer to the source frequency. And if that source then stops, then the f prime is equal to the source frequency. So this says here that detects a sound of continuously decreasing frequency. So it could be approaching the observer, but it would have to be slowing down, not speeding up. So it's not B, it's going to be D. Now, the reason why, this kind of says approaching, and these are the approaching considerations. We also have the receding considerations. So the receding case follows the same logic. If we're receding and the source is increasing in speed, then f prime is less than the source frequency, and f prime gets lower, gets to a lower frequency. Basically, the difference between f prime and f is growing, right? That difference is growing. But if it's receding, moving away, and slowing down, then f prime, the received frequency, is still less than the source frequency, but that f prime is getting higher. Basically, it's approaching the source frequency, or in other words, the difference between f prime and f shrinks. And then if the source decreases to 0, the speed of the source decreases to 0. In other words, if the source stops, then that f prime, the received frequency, will increase until it's equal to the source frequency. So basically, I guess the net takeaway here, let's make it in blue, maybe. So this right here is the net takeaway. The difference in the frequency between the received frequency and the source frequency increases as the speed of the source increases. Whether that source be moving away or moving towards, that's true. I think that's also true if the observer is moving. Like the bigger the speed of the observer, the bigger the difference in the frequency. And so if the source is actually speeding up, then that delta f will actually increase. And if the source is slowing down, then the delta f will decrease. And if the speed of the source is 0, then there is no delta f, but then there is no Doppler effect. And that's number 12, and that is the last multiple choice.
You don't know the first thing about physics. Shut the hell up. Oh, I am.
13A through 13C are not Doppler questions, but 13D is. So they turn off the first speakers. Now we only have one speaker and there's no interference between the two. And it says that B is moving away from the microphone. So by moving away, there's going to be a Doppler shift. So there's the formula for moving a source, and we know that the speaker is moving away. So that means that the received frequency will be lower. So the speed factor would need to be less than 1, meaning that the denominator would need to be larger than the numerator, and so we are adding the speed of the source. Now, one thing to recognize, the speed of the sound I got, eraser, the speed of the sound I got from here, from 13C, speed of sound, 340 meters per second. So, yeah, that's where that's coming from. And so the new frequency, the shifted frequency, is 2986.82, blah, 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 hertz. This is also why not rounding in intermediate steps is important, because when you round the 2986 to two significant figures, you still wind up with 3000. So by two significant figures, there's no shift. But if you subtract 2986.82, etc., from 3000, we wind up with 13. And that's actually what they're asking for, is the difference in the frequencies. And so the frequency shift is 13 hertz. Okay, so the next Doppler question actually deals with this motion sensor that is hitting the bottom plate that a mass is resting on, and that mass is oscillating by moving on or with an attached spring. And so we have some graphs here showing the speed of each test against time. The two different tests says test 1 is with a 1 kilogram mass and spring constant K1. Test 2 is the same experiment with 4 times the mass and a different spring constant, K2. And so there we go. So 14A wants the frequency, then 14B wants the ratio of the spring constants, 14C wants the amplitude of the oscillation for test 1, 14D gets into the potential energy versus time, but then 14E is a Doppler question. It says that the sensor operates by sensing Doppler shifts caused by the motion of the object that it's bouncing off of. So let's go from there. Now, since this is a reflection, it's going to be like the situation with the train and the cliff from before. There's actually going to be two shifts, but it's going to be the same shift every time. There's going to be the shift when the wave reaches from the sensor, when the wave reaches the bottom of the oscillating mass, and then that mass in motion when the wave reflects, that becomes the new source, and there's another shift, but it's an instantaneous shift, so the velocity difference is going to be the same. So this guy here, 14E, I mean, it is 4 marks. Maybe they want you to actually show that the frequency shift is doubled. But anyway, let's break it into 2 parts. We also need to reference the graph, the earlier graph, in order to get the speed. So let's first of all identify some things. It says determine maximum frequency change. So the maximum change in frequency happens when there's a maximum difference in speed between the source and the observer. Now, that would be speed of the source or speed of the observer, because with that chain, the difference in speed, one of the two is at rest. But so let's, before we go back to the graph, I'll make a note that that's what we're looking for. That's important because when we go look at the graph, let's find that graph, not this graph, but this graph. This is the speed versus time graph that it gave us, and the problem did say test 2. So we're looking at the test 2 curve, and I can see that the test 2 curve reaches a maximum speed either with a speed in meters per second, and it has negative values. That should read velocity. That's a fail, because we know speed is a scalar and can't be negative. But whatever, I mean, we get the point. We're just looking for the maximum value, and on either side of this curve we can see that it maxes out at about 9 point. Hold on a second, let me look at this a little closer. There we go. So 9 would be around here, and so it looks like it maxes out at about 9.5 meters per second. All right, so we have a maximum speed value of 9.5. And determining that is one of the 4 marks. And so for the first portion, we have a moving observer because the source of the waves is the rangefinder, and the mass is in motion. So the mass would be the observer. And actually, we know from simple harmonic motion that the oscillating mass hits that maximum speed both when it's moving away from the sensor and also when it's moving towards the sensor. So I think we just have to pick one. I don't think it really matters in terms of the max shift, but we have to choose one. So I don't know, I choose moving away. It's not going to matter. But I think in terms of our reference frames and setting up our situation, we need to choose one or the other. So I'm going to go with, I don't know, my gut says moving away, so it doesn't really matter, so I'm just choosing away. So if it's moving away, then f prime is greater than f, and so our speed factor needs to be greater than 1, so our numerator for moving observer needs to be, we're going to add the speed of the observer. And we wind up with an f prime of 35,977.9, etc. hertz. And I'm not rounding for sig figs yet. I'll do that at the end. And that's for the shift from the sound wave traveling from the sensor to the mass. Now we need the reflection. And we still have the oscillating mass moving away from the sensor. So that would give a, wait a minute, did I mess this up? Hold on a second. Yeah, I messed this up. I have an f prime of greater than the source frequency. That would mean moving towards. Rather than change my math, I'm just going to change our frame of reference, and I'm going to be moving towards now instead of away, because it doesn't actually matter. I'm going to say that I meant to do that as a instructive point, that it does not matter. So I meant to make that change mid-stride, and it's not that I messed up. Right. So anyway, so now we're moving towards the sensor, because again, it does not matter. It hits that 9.5 meters per second in the oscillation, both moving away from the sensor and towards the sensor. And so we're going to get the same frequency change either way. So if I'm moving towards the sensor, then the f prime is going to be greater than the source frequency. The reason why that matters here is because if I'm going to have a higher f prime than the source, and I have a moving source now because of the reflection, then my speed factor is going to have to be less than 1, and so my denominator needs to be greater than the numerator, so I'm going to be, I'm sorry, I said that backwards. I need my speed factor to be greater than 1 in order for f prime to be greater than f. So speed factor greater than 1, so my numerator needs to be greater than my denominator, so I will be subtracting the speed of the source, not adding it. All right, so those are the 2 pieces there. We have the original f prime when the wave reaches the oscillating mass, which is in motion, so that would be the speed of the observer, and that's moving towards the sensor. And I got a upshift for frequency, a new frequency of 35,977.9 hertz. Then it reflects off of the bottom of that mass back towards the sensor. So now I'm using a moving source calculation, where again the source is moving towards the observer, which in this case is the sensor, because the sensor and it's kind of like the same with the train and the cliff face, right? The train was the source of the sound, but then the train also hears the sound. Same with the sensor. The sensor made the sound, it reflected off of the oscillating mass, and now it comes back to the sensor. And so now I'm looking for an f prime here for a moving source, but the source is still moving towards the sensor. So I'm subtracting the speed of the sensor and the denominator on the speed factor. I'm using notice that I'm using the frequency, the f prime, from the original calculation as my new frequency, and then there's another shift. So the actual upshifted frequency f prime may be f double prime. That comes back to the sensor is 3702.012.1, etc. hertz. After all that, I actually forgot what I'm trying to solve for. Something about the frequency. Let's go back to the question. And so they're looking for the frequency change. So the difference between the frequency that returns back to the sensor and the original frequency that came out of the sensor when it went to go do some range finding. And so that would be f double prime minus the original frequency of 35 times 10 to the 3, or 35,000 hertz. And when we control for significant figures, we get a change in frequency of 2 kilohertz, which agrees with the mark scheme. So there you go. First, let's go back to, because we have 4 points here. So we have our first point is identifying the speed. Then the second point is the use of the equations. It says just use one of the equations. I feel like we're going to need both of them. Then the third point is actually solving for those frequencies. And then the fourth point is actually remembering that we're looking for a change in frequency. That's what they asked for. And there's 14E. Look at that. We even fit it all in the box. All right. So now let's go back. Let's go to 15A. State what is meant by the Doppler effect. Okay, 15A. What is the Doppler effect? Okay, Doppler, difference between wave source frequency and observed wave frequency caused by relative motion between the source and the observer. First point is the difference in frequency. Second point is the reason why, because of the relative motion. And what's interesting is that they specifically demand frequency. They said if there's a shift in wavelength, you only get 1 out of 2. Could get into the details on that, but basically, Doppler effect is the only way the frequency of a wave can change, and I think that's kind of important. I know that when waves switch between media, their speed changes and their wavelength changes, but their frequency does not change. But the only way frequency does change, and it's not that the source frequency changes, it's that the observed frequency changes, but it's the observations that matter, because that's when the data collection happens. But anyway, all right, so that's 15A. All right, next Doppler question is actually 15C, but I want to stop off at 15B. Where's 15B? There we go. To say the maximum speed, you have an oscillating plate here, and it says the maximum speed of the oscillating plate is 20 meters per second. We're going to need that in 15C. It says what's the maximum frequency of the sound? In other words, what's the maximum frequency shift of the sound? In order to do the Doppler calculations, we need to know what is the speed of the plate. And the maximum speed we just saw, I already forgot what it is. It's 20 meters per second. Okay, great. And this is a reflection problem, so we have to consider the both moving source and moving observer. Pretty much what we just did, except this one is 2 marks instead of 4, which is kind of annoying if you think about it. So anyway, let's run the numbers. And again, since we're dealing with an oscillation, maximum speed is hit twice. It's in the cycle, and its maximum speed is hit both when the plate is moving away from the source and also when the plate is moving towards the source. Now, this is important and very annoying. I just spent the last about 10-15 minutes solving for the plate moving away, being like it does not matter when the plate hits the Vmax. But keep in mind that this question, the big difference between 15C and the previous 4-mark question we just did, the 4-mark question, I forget what number it was, it doesn't matter, that looked for the frequency shift. 15C wants the maximum frequency received back at the source. So if we're talking about an upshifted, a higher frequency, maximum frequency received. And so if we're looking for a higher frequency, then we have to consider that the plate is moving towards the source so that we get an upshifted frequency instead of a downshifted frequency. So it actually does matter whether the plate is moving towards the source or away from the source. I did not read the question carefully, and so I worked out the entire solution, and I was wrong. All my math and reasoning was right, but it's not what they were looking for. Great, thanks, IB. All right, let's do that. And again, as I've always said, I fell into the trap that I say everyone always falls into by not reading carefully. I didn't read carefully, and so that's on me. Let's redo the solution. This is a reflection, so we're going to need two portions. We're going to need a moving observer and then a moving source. For my f prime, for a moving observer, I'm going to add the speed of the observer so that I have a greater numerator than denominator, so that my speed factor is more than 1, and I will have an f prime greater than the source frequency. For the second leg, I have a moving source. I'm subtracting the speed of the source in the denominator so that my speed factor is greater than 1, because again, I'm expecting an f double prime that is greater than f prime. I use that f prime that I just solved for as my new quote-unquote source frequency, and I wind up with a maximum frequency received back at the source of 2700 hertz, and that does agree with the mark scheme. Phew, I think the two, the two marks are for the two different calculations. So doing the first part to get the 2541 hertz, and then the second part to get the 2700 hertz. And it says you do get 2 marks for just a bald correct answer, but you only get 1 out of 2 if you don't account for the reflection. Okay, so that was 15C. Our next Doppler question is 16D, and we don't need any of the information from the previous questions in order to answer it. So we don't need 15D or 15E or 15F or any of this information here. This is the beginning of question 16, so we're talking about 2 loudspeakers that are going at the same time and have the same amplitude and have the same frequency. So then we have a bunch of things on interference and intensity, but here we are. 16D is a Doppler question. 16D is interesting because it uses the explain command word. So it says, why is the frequency recorded by the microphone lower than the frequency emitted by the loudspeaker? And so the source is actually not in motion. So the Doppler effect here is not caused by the motion of the source, but of the observer. And the reason why the frequency is lower at the observer is because as the observer moves away from the source, the observer is moving and the waves are moving. And so it's not even that there's no actual change in wavelength. There is a change in frequency because there's actually a change in the relative speed of the sound as it's in the medium. Let me show you an example by using the equation for a moving observer. What happens when the observer is actually moving at the speed of sound? It turns out that the observer does not experience the wave at all. So there's the equation for a moving observer, and when we're moving away, we want a lower frequency, and so that means for the speed factor, then the numerator should be less than the denominator. But notice that if the speed of the observer is equal to the speed of sound, then that'd be v minus v over v, so that would be 0, and so the f prime would be 0 hertz. And that sounds strange, but yes, that's true. If the observer is moving at the speed of the sound waves and it's moving away from the source, so are the waves moving away from the source. And so that observer is not actually crossing any wavefronts. And so the observer doesn't actually doesn't experience any of the waves, doesn't move across the waves, it's traveling with the waves. And so it doesn't actually experience the wave. So it's what am I getting at? So the actual explanation I'm going to write in blue. So yeah, as that speed of the observer increases, the observed frequency decreases, because the observer literally experiences the waves less frequently, all the way to the point that if the speed of the observer increases all the way up to the speed of sound itself, f prime decreases to 0, where the observer is not actually experiencing the waves. I like the examiner's report on this question. It says, the majority of candidates answered this question by describing the Doppler effect for a moving source. Others reworded the question without adding any explanation. Correct explanations were rare. So, so that's, in typical, as stated by only an examiner or an invigilator could explain. All right. Anyway, let's move on. And actually, by referencing the equation in that explanation, that makes 16e easier, whereas it actually says to calculate v. V in this case would be the speed of the, it says the moving away from the loudspeaker with a constant speed v. That's a pain in the butt because in the equation they use v for the speed of sound. So we wouldn't want to use any other letter, now would we? No, God forbid. Anyway, so we're going to replace v with uo, with the speed of the observer, but we're going to solve for speed of the observer, and that's what we're doing in 16e. Of course, we're going to need a reference for the speed of sound that is given in the problem. It's given at the very beginning under 16a. The speed of sound is 340 meters per second. So right there it is, for your problem-solving convenience. So we'll put that in. I got that equation backwards. Here we go. We wound up with a speed of the source of 2 meters per second. Our next Doppler question is all the way at the end of 17. So here we're dealing with a simple pendulum. It says the pendulum combines with a stationary object and they move off together. So that's kind of like a ballistic pendulum. Brings me great satisfaction to just wholesale cross out questions. No. All right, 17G, here we go. So we have the speed after the collision of the bob and the stationary object was measured using a sensor. Sensor emits a sound of frequency f, and this sound is reflected from the moving bob. The sound is then detected by the sensor as frequency f. Like, believe it or not, they consider this as sufficient. This is the starting frequency, and then this is the end frequency. Oh, I guess f prime, the prime is kind of like maybe smushed. I think that happened because of QBank. So maybe let's fix that. There actually is a prime there. I didn't see it until I zoomed in. So anyway, there are two different frequencies, and it's like, why are the two different frequencies, the source frequency and the reflective frequency, why are they different? This is an explain question. There are 3 marks. All right, so this is Doppler effect, but it's an explain question for 3 marks, and I give you a lot of room, so let's go. So the first point is that it says mention of the Doppler effect. I just scribbled down Doppler effect. I don't know that we need to actually define the Doppler effect, but your explanation should reflect an understanding of the Doppler effect. So I feel like of the 3 marks, one is, mention the Doppler effect, but then we have 2 different explanations here. One is, or 2 different segments. There's one where the bob as the observer, when it's receiving the waves from the sensor, so that's a moving observer and what's actually happening in that situation. And then the second portion is when the sound waves reflect off of the bob back towards the sensor, then we have a moving source, the source being the bob, and it's a source because it's reflecting the sound waves. So the first portion that I just explained right here is of the moving observer. It says bob experiences a frequency shift from the source as a moving observer. It either experiences the sound waves more frequently if it moves towards the sensor, or experiences those sound waves less frequently as it moves away from the sensor. But then as the sound waves reflect off of the bob, and so the second portion, waves reflect from the bob back towards the sensor experiences a higher f prime if the bob is moving towards the center as kind of like a source that is moving towards the sensor, so the waves have a shorter wavelength and a higher frequency, or a decreased f prime if the bob's moving away from the sensor with a longer wavelength and a shorter frequency. It's unclear if talking about the wavelength is required to get all 3 points. In the mark scheme, it does say you have to talk about the change of the wavelength. I think if you give a sufficient explanation of the Doppler effect, I think you'll get all 3 marks. But again, I want to read to you what the examiners had to say. And it says, with all explained questions, candidates required to go beyond given information. Very few candidates earned marks beyond recognizing that this is Doppler effect. It said some did discuss the change in wavelength, although some candidates chose very vague descriptions like, and I quote, "the waves are all squished up," end quote, rather than using proper physics terms. Some candidates simply wrote and explained the equation from the data booklet, which did not receive any marks. Which, again, that's an equation. It doesn't really explain the phenomena that was observed. And it says, it should be noted that this was a 3-mark question, and yet some candidates attempted to answer it with a single sentence. So that's kind of a savage burn from the examiners, being like, yo, we're saying explain here, we're giving you a lot of room, and if you're going to jot down 1 sentence, that fail is on you. All right, heard. Okay, so that was 17G. That was the end of number 17, and so we're getting towards the end of these question sets. Let's see what 18 has to offer. I can tell that 18A is a fringe question. I think that was 9.3. Why does it need to be coherent? We saw this question already. Wavelength, separation, calculate D. Nope, that seems to be like a 9.3 question to me. Then we have a diffraction pattern, angular separation, deduce the width of one slit. I'm still waiting for the Doppler part. Wavelength of the light emitted by the galaxy is 621.4 nanometers. Explain without further calculation what can be deduced about the relative motion of the galaxy and the Earth. Boom, here is my Doppler application. The wavelength emitted by the galaxy is 621.4 nanometers. What can be deduced about the relative motion of the galaxy and the Earth? Well, I would deduce that there's a redshift because like everything is redshifted, but that's not good enough. So let's see. Can I find out what the source wavelength is, and then I can compare that to the received or observed wavelength. That's interesting. That actually, I did not read that correctly. That is the source emission. It says the wavelength as emitted by the galaxy is 621.4 nanometers. But it says over here at the beginning of the problem, not at the beginning, near the beginning of the problem, in 18C, that the wavelength as observed on Earth is 633 nanometers. So that is the observed wavelength. All right, so the observed wavelength is greater than the source wavelength, and so the observed wavelength, that would be, as I predicted, a redshift. And we know from the Doppler effect that if the source and the observer are receding, then the observed frequency is less than the source frequency, and since wavelength is inverse of frequency, the received wavelength is longer than the source wavelength. So seeing that the received wavelength is longer than the source, what can be deduced about the relative motion of the galaxy and the Earth? They are moving apart. That's it. Thank you, number 18. Let's wrap up with number 19. The first point is saying that the galaxy and the Earth are moving apart. This does say explain. This is actually a pretty simple explanation question, but you do need to say the galaxy and the Earth are moving apart, but the second point is why that's true, and we can see based on the wavelength that the observed wavelength is longer than the source wavelength. And actually, I'm going to go to the end of the worksheet, and this is 9.4 that just resolved. We just did this with the aircraft being just resolved. So our very last question is 19A, but they're going hard here. They got 3 different levels, I, double I, and triple I. for 6 marks. Booyah. Okay, let's go. All right, so this is a 6-mark question, but really it's 3 questions, 2 marks apiece. So 19 AI, explain the reason for the frequency change. Well, it's the Doppler effect, but it's an explain question, so let's get into it. So the moving car experiences the source waves at a f prime different than the source frequency. If the source and the wave are approaching, the source and the observer are approaching each other, the observer experiences the waves more frequently than the source is emanating, and if the observer is receding, moving away, it experiences the waves less frequently than the source is emanating. So that's the frequency shift. Now there's a factor of 2 in the frequency change equation because of the reflection. So yeah, waves reflected from the car, so there's one shift with the car as the observer of the original wave, then there's another shift as the wave reflects and the car is now the source and the cop is the observer. So there's basically 2 shifts that occur. And then it says triple I, determine whether the speed of the car is below the maximum speed allowed. Maximum speed is 28 meters per second. And so they give the transmitter frequency and they give the delta F. So basically we just use the equation they gave us to solve for V, the speed of the car. All right, so we're solving for V, so that'd be the speed of light in a vacuum, or in air, close enough, times the shift in frequency over 2 times the source frequency. We have the shift and the source frequency given here. 40 gigahertz is the transmitter frequency, and the shift is 9.5 kilohertz. And so I reflected that in our powers of 10 here. So let's solve for the speed of the car. And so when we round to 2 significant figures, we get that the car is going 36 meters per second. The limit is 28 meters per second, so that is well over the limit. Time for a speeding ticket. Yep, and actually you do need to say, because it did ask in the question, determine whether the speed of the car is below the maximum speed allowed. So technically, to answer the question precisely, the speed of the car is not below the maximum speed, it is above the maximum speed. I found that with these questions that if they say something specific, like is the speed of the car below the maximum speed, and you don't answer the question, be like, no, the speed of the car is not below the maximum speed, they may actually ding you on that point. So there it is, the speed of the car is not below the maximum speed allowed, it is above the maximum speed allowed. Okay, but I believe that is the end of our Doppler questions. There were a lot of pages in that situation there, but we are finito with almost an hour and 15 in this video. Yeah. Thank you.